Hey everyone, I'm Sean, co-founder and CTO at Cerebras Systems. Now, when we started Cerebras, we had a vision to drastically change the landscape of compute for AI. And today, I'm going to show you how next generation AI is uniquely enabled by our GPU impossible performance. Now, if you're not familiar with Cerebras, we started in 2016, really at the beginning of the modern deep learning era. And what an exciting last few years it's been for the entire industry, but also for us as a company. We now have engineers and customers all around the world. Now, at the heart of Cerebras is our chip, the Wafer scale engine. Shown here is the third generation. It's the largest chip ever produced. At over 46,000 square millimeters in size, we can pack 4 trillion transistors. All right, that's 900,000 compute cores for a total of 125 petaflops of AI compute, all on a single chip. Yeah, that's definitely something to cheer for. And because it's all on a single chip, we have some truly mind-boggling performance numbers for memory bandwidth and fabric bandwidth. Now, we don't just build chips. Around each one of those wafer scale engine chips is a specially designed system, the Cerebras CS3. And we build supercomputer clusters with these systems. With hundreds of systems, we now have 4 clusters, the largest of which is coming up now in Minneapolis with 64 exaflops of AI compute. Now, in every one of those systems is the wafer scale engine chip that is 56 times larger than the largest GPU today. 56 times larger. Now, to understand the significance of that, I think it's really important to think about this in the historical context. And it's actually really appropriate because we are today standing in the Computer History Museum, right? Over the last 50 years, since the beginning of the semiconductor chip industry, every single chip has followed a predictable trend. The transistor count doubled every 2 years. Every single chip that has been produced in the last 50 years follows this trend. This is Moore's law. We all know it. And this is what defined what is possible in the semiconductor industry. Until now. Because the Cerebras wafer scale engine is the chip that broke Moore's law. The wafer scale engine in the Cerebras CS3, which is available today, is like having a GPU from 10 years in the future. Now, this is a really big deal, not just because we solved a fundamental challenge in the chip industry, but this is a really big deal because it enables next generation AI applications that are not possible otherwise. Let me show you what I mean. Let's look at the problem of generative inference. Now, this is a really interesting problem because if we take all of the LLMs in use today and we graph their output performance, something becomes immediately obvious. Generative inference today is really, really slow. Now, there's so many different ML model designs, and there's so many different hardware architectures running those models. So why is the performance all so similar? Now, the answer to that is really, really interesting. Because even though there's so many different hardware designs, they are all limited by the same thing. They're all limited by the memory bandwidth to their HBM memory. This is the HBM memory wall. And at Cerebras, with our unique wafer scale architecture, we will enable the entire industry, the entire community, to break through this memory wall and enable a level of generative inference performance that's never been seen before. Let me show you what that looks like. Now, this is the popular Llama 70B model. This is a chatbot interface demo where we have Cerebras on the left, and we have GPUs in a DGX in a hyperscale cloud on the right. It's the same model, the same prompt. Now, watch really closely because you might actually miss this. You press go, and Cerebras is done, and we're waiting for the GPU. Now, if you've used a chatbot before, like ChatGPT, this experience might be familiar. We're still waiting. We're still waiting. Still waiting. Now, finally, the GPU is done. Now, what we all just witnessed is the fastest inference on the planet. On Llama 70B, on Cerebras, we are running over 2,000 tokens per second. That's up to 70 times faster than hyperscale cloud GPU solutions. This is GPU impossible performance. 70 times faster than GPU solutions today. Now, it's important to note that this isn't just because we're comparing to 8 H100s in a DGX. No number of GPUs can achieve this level of performance. And let me show you why. The reason is that the Gen AI inference problem is a memory bandwidth problem. To generate 1,000 tokens requires 1,000 serial passes through the model. And every single one of those passes requires reading all of the model parameters from memory. And so if you have relatively low memory bandwidth, it becomes the bottleneck for generation performance. It's just that simple. And this is why wafer scale matters. Because of all the resources we have on our massive chip, we have a massive amount of memory bandwidth. 21 petabytes per second of memory bandwidth. That's 7,000 times more than an H100. Now, with that level of memory bandwidth, we can completely remove the memory bandwidth bottleneck. So when you zoom out, this all starts with our core. Our core has tightly coupled compute and memory. On the compute side, we have high-performance tensor operations, both 16-bit compute data paths and 8-bit compute data paths. We have fast instructions for nonlinear functions, and we have fine-grained data flow scheduling for all the instructions. Now, this is really important because this allows us to have native unstructured sparsity acceleration, something that's unique to the Cerebras architecture. Coupled with that compute, we have high bandwidth memory and cache. We have 48 kilobytes of SRAM for every core and 512 bytes of local cache. And then, most importantly, from that memory, we have full bandwidth to the compute data path for full compute performance. Now, what we do is then we take that core and we tile it out 10,000 times in a die. Every one of those die is like a traditional chip. Then we tile out 84 die in a wafer for a total of 900,000 cores. And then we connect those die together. This is where the wafer scale integration magic happens. We invented this process of connecting die and crossing the reticle boundary in our first generation wafer scale engine in collaboration with TSMC. And now we've extended it to the 5-nanometer process. Now, you can probably already tell, to do this requires co-design with the fabrication company, TSMC, with the die-level fabric design, and with the system. Because every one of these die have a 2D mesh fabric that connects all of the cores together. And then what we do is we extend that mesh fabric across the die boundaries. And here's the key. We do that at full performance because this is all on chip. And this forms a uniform fabric at both the die level and the wafer level. This is how we can get the entire wafer to operate as a single chip. Now, to manage yield, we have built-in hardware redundancy to route around failures so that the software always sees a uniform 2D mesh fabric. So when you zoom out, what we have is a wafer scale, SRAM-based compute in-memory architecture. The reason we can get 7,000 times more memory bandwidth than a GPU is because our compute is embedded inside the memory. If you compare that with a GPU, its compute cores access memory by going over an external memory bus to external HBM. Now, on the GPU side, you may be familiar with this. They attempt to achieve higher aggregate memory bandwidth by integrating multiple GPUs together, specifically 8 GPUs in a DGX server. Then they access these GPUs all in parallel so you can get higher aggregate memory bandwidth using a technique called tensor parallel execution. This gives 8 times higher aggregate memory bandwidth. But it comes at a cost. It comes at the cost of hundreds of high-speed serial links, of multiple interconnect switch chips. It comes at a high dollar cost, but also a high power cost. We estimate there's about half a kilowatt of power in all of this interconnect alone, just to connect GPUs together. So, when you compare multi-GPU integration with wafer scale integration, the difference is just staggering. Even with 8 times higher aggregate memory bandwidth in a DGX, a single wafer scale engine chip still has 800 times more memory bandwidth. And what's more, we do that with 33 times higher I/O and 6 times lower absolute power. Now you might ask, how is this even possible? The answer is actually really simple. And the reason is, if you think about it, in a DGX, for the GPUs to communicate to one another, they have to transfer data across hundreds of serial links. They have to move that data across multiple connectors, circuit boards, switch chips. Now you compare that to the wafer scale engine, where we are moving data less than a millimeter on silicon. It's just physics. Now, what's more is that multi-GPU performance doesn't even scale that well. You get higher aggregate memory bandwidth on paper, but in reality, tensor parallel execution actually doesn't even scale that well for generative AI performance. And the reason for that is that all of that interconnect that we just looked at, it has bandwidth and latency overheads. What I've plotted here is the memory bandwidth utilization of Llama 70B running on GPUs within a DGX server. Now what you see is that when you run on 2 H100s, they're achieving about 60% memory bandwidth utilization. Now, for those who are used to optimizing software, this is actually pretty good. But when you scale that to 8 H100s, that utilization drops to 25%. Now, keep in mind that this is all on the highest performance interconnect within the DGX server. This is the reason why multi-GPU architectures do not scale performance well for Gen AI inference. Because going from 2 GPUs to 8 GPUs, that's 4 times higher aggregate memory bandwidth, in theory, 4 times higher. But they're only getting 1.7 times higher performance. That's only 42% scaling efficiency. Now, this is also the reason why GPUs do not scale well beyond a DGX. Because when you go beyond the DGX server, the performance drops even further, which limits scaling. Performance scaling plateaus after 8 GPUs. You can add more GPUs and use them to run more instances of the model, but you cannot use them to accelerate and run the single model faster. This is illustrated in this graph, where I'm plotting Llama 70B performance versus the number of GPUs that you use, and you can see it plateaus after 8 when you go outside of a DGX. Now this is Cerebras' performance. We're 70 times faster, and this is the reason no number of GPUs can achieve this level of performance. Now, let me show you how we achieve this ultra-fast generation performance. Since we have so much memory bandwidth, we can actually use the opposite execution model as GPUs. As I just mentioned, on GPUs, you use multiple GPUs together in parallel to run a single layer so that you can get higher aggregate memory bandwidth. But on Cerebras, we have so much memory bandwidth, we can use just a fraction of the chip to run a single layer. Now, the way we do that is we map the ML model as a hardware pipeline on the wafer. Every model layer is mapped to a wafer region, and each one of those regions is sized based on the compute and memory requirements. We keep the weights and the KV cache local, physically in that region, so it's close to the compute. And then we just execute it as a low latency pipeline. Every region processes 1 token. And remember, we have enough memory bandwidth to run such that we can feed the compute data path at full speed, so we can run with a local batch size of just 1. We also have the local fabric that enables ultra-low latency. Now, once the layer is complete and finished processing that token, the token moves on to the next layer. And we place that next layer in the physically adjacent region so there's virtually no latency between layers. Now, this is only possible because this is all done on chip. Now, we keep executing this way, layer by layer, until the final layer, which generates the output token. That's what goes back to the user, and we cycle that back into the beginning of the model to generate the next token, and we repeat the process. So this is the pipeline execution model that enables ultra-fast token generation. This is the pipeline execution model that enables what we all experienced earlier, the fastest inference on the planet, up to 70 times faster than hyperscale cloud GPU solutions. 70 times faster. Now, what does 70 times faster speed enable? Here's an example. We've probably all experienced this multiple times every single day. Here's Google's Gen AI search application. You ask it a question, And then you press go, and then you wait. And then you wait. And then you wait. And finally, you get your answer. Today, Gen AI applications are very promising. That answer is actually pretty good. But they're all so slow, meaning they have limited user engagement, making them very primitive. 70 times faster speed eliminates that wait. You get more interactive responses for higher user engagement. For Gen AI applications to be truly interactive, they require substantially faster responses. Imagine that Gen AI search application that we just saw, but instead of waiting 5 seconds for the entire response, you get the entire response in less than 1/10 of a second. Or imagine a generative voice application where today it might sound very unnatural because responses take as high as 700 milliseconds. Imagine getting those responses in 10 milliseconds. 70 times faster speed will lead to the most engaging and the most interactive applications. But it's not just that. The entire industry, the entire community is moving towards agentic and chain of thought frameworks, where a single request can require multiple LLM calls. OpenAI's recent O1 model is an example. These are emerging models that can reason, and they can take longer by actually doing additional steps. They can plan, they can strategize, they can even self-reflect and change their own outputs. But every single one of these additional steps adds compute, it adds LLM calls. For a model like O1, it's very reasonable to take 10 times more LLM calls in the background for every request. And then if you combine that with an agentic framework, it's very reasonable for a single request to require 100 LLM calls in the background. So in that context, 70 times faster speed will enable better and higher quality models. It will enable more agentic and more chain of thought reasoning. It's very clear that faster response is required to make these emerging applications even viable. Imagine a complex AI agent application today that, because of all the iteration, might require 70 minutes of processing time. For a lot of applications, that may not even be viable. Imagine doing that in 1 minute. Imagine a chain of thought application like O1, where in the same amount of time as it takes today to do 10 reasoning steps, you can do 700 reasoning steps. Imagine the capability of that model. 70 times faster speed will enable the most powerful, the most sophisticated, and the most engaging applications. And you know what? This need for speed is even more evident for larger models. This is the Llama 405B model. It's about 6 times larger than the model I showed earlier. It is currently the largest, the highest quality, state-of-the-art model in the open source community. Same chatbot demo, Cerebras on the left, hyperscale cloud GPUs on the right. Same model, same prompt. You press go, Cerebras is done, and you're waiting for the GPU. In fact, I think Cerebras finished even before the GPU even started. And you're still waiting, and you're still waiting. This is actually going to go on for a long time. This is painfully slow. Now, what's more, is that not only is it very clear this is not a good user experience as a chatbot, but imagine it's not a human that's waiting for this output, right? Imagine it's an agent that's waiting for this GPU output in the background multiple times, 10 times, 100 times, before any response is given to the user. I mean, it's still going. Well, such a product wouldn't even be viable. But it is viable on Cerebras. Because again, what you just witnessed is the fastest inference on the planet. Llama 405B running at approximately 1,000 tokens per second. Again, up to 70 times faster than hyperscale cloud GPU solutions. Llama 405B running 70 times faster. This is something really special. Let me put it in context. Here's a graph of model quality versus output speed on GPUs. Now, what you see is that tiny little models, like this 1 billion parameter model on the bottom right, they run pretty fast on GPUs, over 500 tokens per second. But the quality is very low. It's not a very good model. Very expected, since it's only 1 billion parameters. All of the best models are up here. All of the frontier models are up here. These are GPT-4o, Claude, Gemini. They have the highest quality, but they're very slow. This is Llama 405B running on GPU. And this is Llama 405B running on Cerebras. Llama 405B on Cerebras is the world's fastest frontier model. In fact, it's even faster than the 1 billion parameter model running on GPU. Cerebras 405B is the first frontier model that runs instantly. This is something special. So now, as we wrap up, I pose the question to all of us. What can we do with this? Well, I believe this will enable next-generation AI applications like the ones I just showed you. But I also believe that this level of performance, this massive leap forward, will enable a whole new class of Gen AI applications that we can't even imagine right now. And we at Cerebras, we can't do this ourselves. As a community, let's build the next generation AI application together. And at Cerebras, we're doing our part. Everything I just mentioned today, it's available in the cloud right now. Cerebras inference service is available right now at inference.cerebras.ai. There's a chatbot interface, there's an API interface. We have Llama 8B, 70B, and 405B with both an exploration tier and an enterprise tier. We also have Mistral's models and many new models coming soon. So with this, we all as a community have access to GPU impossible performance. You all now have access to GPU impossible performance to build your next generation AI application. And I can't wait to see what you come up with. Thank you very much.